Okay, welcome back, students. Let's go ahead and get into chapter 10, our last chapter here, section 10.1. Share my screen. Okay, 10.1 and all of chapter 10 is on the Laplace transform. Okay, definition. Let f be a function defined on an interval from 0 to infinity. The Laplace transform or Laplace transform of f is the function f of s defined by f of s is equal to 0 to infinity, 0 to infinity of e to the minus s t f of t dt, provided the integral converges the Laplace transform of f will be denoted by L of f. So determine the Laplace transform of the following functions. Okay, A. F of t is equal to 1. Okay, so we'll call that L of 1, okay, which is equal to the integral from 0 to infinity of e to the negative st times 1 dt. Okay, so s is just treated as a constant here. And so this is going to become negative 1 over s e to the negative st from 0 to infinity, which is the limit, okay, as n goes to infinity of negative 1 over s e to the negative st from 0 to n, okay, which is the limit as n goes to infinity of negative 1 over s e to the st, okay, minus negative 1 over s e to the, that's n, my bad, e to the Sn, okay, minus 1 over S e to the negative S times 0. Okay, so this limit as n goes to infinity, well, this thing's just going to go to 0. This thing is going to go to 1. And so I'm just left with positive 1 over S. So 1 over S. So that tells me that L of 1 is equal to 1 over S, given that S is greater than 0. Okay. S can't be 0, and S needs to be positive. Okay, and so yeah. Okay. If S was negative, then it would not converge. Okay, because I'd end up with a negative times a negative here, and that would give me a positive, and that thing would not go to 0. Okay, so just letting you know why S has to be positive. Okay, B. What about f of t is equal to t? Okay. So we're going to see that we're going to kind of build these Laplace transforms. The constant building block is 1 over S, and now this first this linear building block is t. Okay, so t to the first power. Let's see what we get for t to the first power. So we're going to say L of t is equal to 0 to infinity of e to the negative st t dt. Okay. So now this one's not as simple. This is integration by parts. So u is equal to t, du is equal to dt. Okay, dv is equal to e to the negative st, and v is equal to negative 1 over s e to the negative st. Okay, so u v v du is going to be negative t over s e to the negative st, okay, minus the integral of negative 1 over s e to the negative st dt. Okay. So this goes from 0 to infinity, and this is still 0 to infinity. Okay, so if I integrate negative 1 over s e to the negative st, then I'm just going to do the same thing twice, and that just becomes minus positive 1 over s squared e to the negative st. Okay, and this is negative t over s e to the negative st. All of that is evaluated from 0 to infinity. Okay, so I'm going to take the limit as n goes to infinity of, okay, this guy here, negative t over s. What did I do it before? Okay, oops. E to the negative st minus 1 over s squared e to the negative st from 0 to n. Okay, and so let's plug in our n's and zeros. And so limit as n goes to infinity of negative t over s e to the negative s n minus 1 over s squared e to the negative s n minus negative t over s. Oops. Sorry, this should be n. Oh, my bad. Negative 0 over s e to the negative 0 s times 0 times 0 minus 1 over s squared e to the negative s times 0. Okay. Okay, and when we reconcile that, okay, so this guy, let's just do the easy stuff first. That guy's going to go to 0. Okay, the limit of that is going to go to 0. Okay, and then this guy over here, this guy's going to go to 0 because we've got 0 times something. That's going to go to 0. Okay, I have the limit. Okay, as n goes to infinity of negative 1 over, whoops, negative n over s. And I'll just do e to the Sn. Okay, and then plus 1 over s squared. Yeah, this just goes to 1. So that's just plus 1 over s squared. Okay. So I really need to know, well, what's happening with this guy, and we're going to use the L'Hopital's rule to help us solve that. Okay, so this is equal to, using L'Hopital's rule, the limit as n goes to infinity of the derivative of the top is going to be, let me just look at this part, because that's the only part that has n's involved. Okay, limit as n goes to infinity of the derivative of the top is 1, and the derivative of the bottom is just s squared times e to the Sn. Okay, and so now I don't have infinity over infinity, which I had before. Okay, before I had infinity over infinity, so now this thing just goes to 0, and I'm just left with 1 over s squared. Okay, so L of t is equal to 1 over s squared when s is greater than 0. And in general, we could generalize this as kind of a power rule, and we could say that L of t to the nth power is equal to, okay, through successive integration by parts, n factorial over s to the n plus 1 power. S is greater than 0. Okay, C. Let's look at C here. Okay, f of t is equal to e to the at. Okay. Let's see what we get when we have an exponential, e to the at. Okay, so we want the Laplace transform of e to the at equals integral 0 to infinity of e to the negative st times e to the at dt. Okay, let's combine the e's. Oops. 0 to infinity of e to the a minus st, or what I probably want to do is think of that as a negative. So I'm going to just leave it as negative s plus a. Okay. Right now, t dt. Okay. And then I'm going to change this again. I'm going to factor out a negative. Okay, just so that it gets the right form that I want. E to the s minus a t dt. Okay, so I have a negative there, which is nice. Okay, because I'm going to want to take a limit of that, and if it's negative, then that thing's going to go to 0. Okay, so let's integrate this. S minus a is negative s minus a. That's just a okay. Then this thing, when I integrate, s minus a, again, negative s minus a is just a constant. That's what I meant to say. Okay, so this is going to be 1 over negative s minus a times e to the negative s minus a t. Okay, evaluated from 0 to infinity. Okay. And so I'm going to take the limit as n goes to infinity of 1 over negative s minus a over e to the s minus a times t, okay, from 0 to n. And so this is the limit as n goes to infinity of 1 over negative s minus a e to the s minus, let's plug in the, yeah, e to the s minus a n minus 1 over negative s minus a, okay, e to the s minus a times 0. Okay, so this thing here, if I take the limit as n goes to infinity, that becomes 1 over infinity, which is just 0. And then this thing here, the e to the s minus a, can't really see that. E to the s minus a times 0, that just becomes 0. E to the 0 is 1. So this becomes positive 1 over s minus a. Okay, given that s minus a is greater than 0, however, I could toss the a to the other side and I would just have s is greater than a. So let me rewrite that as s is greater than a. So that's the Laplace transform for e to the at. Okay. Okay, let's do another one. Okay, let's try a trigonometric function. Okay, d. The Laplace transform of sine of bt, okay, is equal to 0 to infinity of e to the negative st sine bt dt. Okay. Okay, so we're going to do a couple of integration by parts, and then we're going to use that trick where sine, the integral of sine goes to cosine, and then the integral of cosine goes back to sine. So we're going to use a trick of the fact that this thing oscillates, okay, and that we'll get back to something that resembles our original integral. Okay, so let me do a u substitution on this, or not a u sub, integration by parts. U is equal to, I'm going to use light, so the trigonometric comes before exponential. Okay, logarithmic, inverse trig, algebraic, trigonometric, and exponential. So trig comes before exponential. So u du, u is equal to sine bt. The derivative of that is going to be b cosine bt. Okay, dv is equal to e to the negative st. V is equal to negative 1 over s, e to the negative st. So this is dt. That's dt. Okay, so u v v du, that's going to be, I'm going to write this as over here 0 to infinity of e to the negative st sine bt equals, okay, negative 1 over s e to the negative st sine bt minus the integral of negative b over s e to the negative st cosine bt. Okay. dt. Okay, so now I'm going to do another u sub, or not u sub, I keep saying that. Another integration by parts. Okay, so this thing is equal to, okay, negative 1 over, let me just reconcile this negative sign. E to the negative st sine bt. Okay, plus, I'll pull that negative outside, plus the integral from 0 to infinity. This goes from 0 to infinity. Okay, 0 to infinity of, and I might just leave this as 1 over s e to the negative st b cosine bt. I'll keep those b's together for right now. dt. Okay, so let's do another another integration by parts. U is equal to b cosine bt. Du is equal to negative b squared. Okay, sine bt. Okay, dv is equal to 1 over s e to the negative st dt. And v is equal to negative 1 over s squared e to the negative st no dt. Okay, so now this becomes negative 1 over s e to the negative st sine bt plus or minus in this case, minus b over s squared cosine e to the negative st cosine bt. Okay. Okay, and then this would be minus, and then I've got 3 negatives here. Maybe I'll just go like this for right now, just to keep the negatives reconciled. I'll do plus that minus the integral of 0 to infinity of negative 1 over s squared e to the negative st times negative b squared times sine bt dt. Okay, so now I want to reconcile all these negatives here. Okay, this is equal to, okay, remember what is it equal to? The original was 0 to infinity of e to the negative st sine bt. Okay. And so we get negative 1 over s e to the negative st sine bt minus b over s squared e to the negative st cosine bt. And then I've got three negatives here. Okay. And so I can reconcile those three negatives by just putting one negative on the outside. This negative and this negative cancel. Okay, so this is, and then what I'm going to do is I'm going to factor out the b squared and the 1 over s squared. So this is minus b squared over s squared times the integral of 0 to infinity e to the negative st sine bt dt. And that's really what we started off with. So what I can do is I can add b squared over s squared 0 to infinity of e to the negative st sine bt dt to both sides, b squared over s squared 0 to infinity of e to the negative st sine bt dt. Okay, is equal to, this thing goes away. Okay, I'm going to add these, add those together. And I get 1 plus b squared over s squared times 0 to infinity. Okay, e to the negative st sine bt dt is equal to negative 1 over s e to the negative st sine bt minus b over s squared e to the negative st cosine bt. Okay, let's find a common denominator here. Okay, and we're going to end up with s squared over s squared, which is just s squared plus b squared over s squared. Okay, times this guy, 0 to infinity e to the negative st sine bt dt is equal to negative 1 over s e to the negative st sine bt minus b over s squared e to the negative st cosine bt. Okay, and so if I just divide by s squared, divide by this, s squared over b squared over s squared, I will end up with 0 to the to infinity of e to the negative st sine bt dt is equal to s squared over s squared plus b squared times negative 1 over s e to the negative st sine bt minus b over s squared e to the negative st cosine bt. Okay, and that's all evaluated from 0 to infinity. Okay. Okay, so this is equal to, okay, the limit as n goes to infinity of okay, s squared over s squared plus b squared times negative 1 over s e to the negative st sine bt minus b over s squared e to the negative st cosine bt. Okay, I'll evaluate it from 0 to n now. Okay, so this is equal to, okay, the limit as n goes to infinity of s squared over s squared plus b squared, okay, times 1 over s, negative 1 over s e to the negative st times the, sorry, it's no longer t, it's n, Sn sine of Bn minus b over s squared e to the negative Sn cosine n of Bn. Okay, okay. Minus s squared over s squared plus b squared times negative 1 over s e to the negative s times 0 sine of b times 0, okay, minus b over s squared e to the negative s times 0 times the cosine of b times 0. Okay. Okay, it looks interesting. Nice. Okay, so what do we get for our next line? Limit as n goes to infinity. Okay, of s squared over s squared plus b squared times negative sine bn over s e to the sn. Okay. Okay, and I'm not going to do it here, but we can prove from the squeeze theorem that this thing is going to go to 0. Okay, because the sign is bounded between 1 and negative 1. Okay, since negative 1 is less than or equal to sine bn, which is less than or equal to 1. So it's bounded between 1 and negative 1. Therefore, I could prove through the squeeze theorem that that thing is just going to, if I were to divide everything by e to the sn, e to the sn, and e to the sn, okay, I could prove that this thing's going to go to 0. If I take the limit as n goes to infinity, that thing goes to 0, that thing goes to 0, and then therefore by the squeeze theorem, that guy goes to 0 as well. Okay, so I guess I did kind of prove it. Okay, informally. So it's kind of an informal proof of why that goes to 0. Okay, we could say the same thing about the cosine. It's basically the same argument. E to the Sn over cosine Bn. Okay, that goes to 0 by the same argument. Okay, and so then I'm left with negative s squared over s squared plus b squared. Okay, the sign of 0 goes to 0. So this thing goes to 0, which wipes out that thing, which goes to 0. That whole thing goes to 0 because the sine of 0 is 0. Okay, and so this is that times negative b over s squared, okay, times e to the 1, and then cosine b to the 0 is just 1. So this is 1, and this is 1. So 1 times that is just that. And so this becomes, okay, equal to, everything in the first term goes away. And then it's just that the s squareds are going to cancel here. And I'll just be left with b over s squared plus b squared. Okay. So the Laplace transform for the sine of bt was equal to, okay, b over s squared plus b squared. Okay, by a similar method, okay, by a similar method, basically the same method, it can be shown that the Laplace transform for cosine of bt is equal to s over s squared plus b squared. So sine has the b on top, and cosine has the s on top. Cool. So we've done we've shown Laplace transforms for powers, constants, and exponents, and trigonometric. That's good. Okay. Let's look at some properties of the Laplace transform. So properties of the Laplace transform. Okay, L of f plus g is equal to L of f plus L of g. Okay, and then the Laplace transform of a constant times f is equal to a constant times the Laplace transform of f. Okay, definition. A function is piecewise continuous on AB if we can divide AB into finite subintervals such that, okay, 1, f is continuous in each subinterval, and 2, f approaches a finite limit at each of the endpoints. Finite limit as each of the endpoints of each subinterval or approach. Or approached. Okay, it can't go off to infinity. Okay. Okay, so what's an example of piecewise continuous? Okay, if I've got three subintervals, okay, and I can have something that looks like this. Okay, and then maybe it goes there. Okay, and then it goes like this. Okay, and so we don't really care what happens at the break in the continuity, except for the fact that we have limits there. Okay, we can't go off to infinity. So this is called piecewise continuous. Okay, what is not piecewise continuous is if we have, okay, three subintervals, and say something goes off to infinity or has an asymptote, then that is definitely okay, not piecewise continuous. Okay, theorem. Oops. Okay, all piecewise continuous functions have a Laplace transform. Okay, because in between the pieces, we have really nice functions. No weirdness going on. Okay, so example number 2. Okay, find the Laplace transform of t of f of t, sorry, is equal to t from 0 to 1, and it equals -1 when t is greater than 1. Oops. Yeah, it's fine. Okay, so it's linear from 0 to 1, and then it becomes a constant function after 1. Okay, so the Laplace transform of the function is going to be equal to, okay, in this case, it's no longer 0 to infinity for that t value. Okay, so it's from 0 to 1, which kind of changes things. Okay, this is e to the negative st times t dt plus the integral from 1 to infinity of -1, which is negative, we'll go like this, e to the negative st times -1 dt. Okay, so we're not going from 0 to infinity anymore. We've got this kind of thing broken up. So it is going to affect what the Laplace transform is going to be. Okay, so let's do integration by parts on this guy. U is equal to t, du is equal to dt, and dv is equal to e to the negative st dt, and that means v is equal to -1 over s, e to the negative st. Okay, bump. We get t, negative t over s, e to the negative st, okay, minus the interval from 0 to 1 of negative 1 over s, e to the negative st. This goes from 0 to 1. Okay, for that first part. Okay, so we've got negative t over s, e to the negative st, minus the integral of this is going to be another 1 over negative s. So that's going to become negative 1 over s squared. I basically end up with 3 negatives. Okay, e to the negative st from 0 to 1. The whole thing is going to be 0 to 1. Okay, plugging in 1, I get negative 1 over s, e to the negative s. Okay, minus 1 over s squared, e to the negative s. Okay, minus, plugging in 0, I get negative 0 over s, e to the negative s, which is going to go to 0. S times 0. Okay, and then minus 1 over s, e to the negative s times 0. Okay, so this thing goes to 0. Okay, and so I'm just left with negative 1 over s, e to the negative s, minus 1 over s squared, e to the negative s, okay, plus okay, distribute the negative, plus 1, e to the 0, which is 1. So this just becomes 1 over s. Okay, so that's the first portion. Let's do the second portion, which is a little bit easier of an integral. This just becomes negative 1 times 1 over negative s, e to the negative st, evaluated from 1 to infinity. Okay, so these negatives are going to cancel each other out. Okay, and so I'm just left with the limit as n goes to infinity. 1 over s, e to the negative s n. Well, let's do s t as we go from 0 to n. As t goes from 0 to n. So this is the limit as n goes to infinity of 1 over s, e to the negative sn, minus 1 over s, e to the negative s times 0. And so this thing is going to go to 0. Okay, I mean, I could have written it like this. Okay, but you basically understand that this thing is going to go to 0. Okay, when I take the limit, and this thing's going to go to 1, e to the negative s times 0 goes to 1, and 1 times negative 1 over s is just negative 1 over s. Oh, you know what? This isn't 0. This is 1. I'm sorry. It should be 1. Okay, and so this becomes minus 1 over s, e to the negative s. Okay, which this guy is going to combine with this guy to give me negative 2 over s, e to the negative s, minus 1 over s squared, e to the negative s, plus 1 over s. And that is the Laplace transform of that piecewise function. Okay. Okay, and that's 10.1 there. I'll see you in the next video.